We're now ready for the precise definition of limit. We're first going to get a sense of what it would need to say looking graphically, and then we'll have it formally presented. Let's look at y equal 2x minus 1 near the value of 4. Now the question is, how close to 4 do we need to be if we needed to be within 2 units of the limit at 4? Well, graphically we can see here's the limit at 4, and if we went 2 above that, or 2 below that, as long as we picked an x value so that the function value would fall somewhere in this region, we would be within 2 of the limit. So looking here, we could see if we picked, for example, x equal 2 and we went and found the function value, we are more than 2 away from the limit. And if we picked something like x equals 6 and we went and found the function value, again we're more than 2 away. But we could see if we picked anything between 3 and 5 that when we found the function value we'd be within 2 of the limit. So as long as on 4 we went within 1 on either side, the distance from our function value to the limit would be less than 2. Now we could call distance from the function value to the limit epsilon. That's just a Greek letter. Say that if we take the difference between the function and L, so we've got that absolute value, and subtract, so that would give us the distance, is be less than epsilon here. And we're going to call that little distance here from x, how close to x we need to be, delta, another Greek letter. And we have the distance from x to a with x not equaling a less than delta. So basically, as long as we get close enough to x, if we get within delta of x, then we know that our function value is going to be within epsilon of L. In order to satisfy this restriction, we have to be within epsilon. How close to x would we need to be to have this happen? We can restrict the x values to that. So what if it was 1 instead of 2 as we're looking here? We could be as far as 1 above or as far away as 1 below, and we have this little region here. How close to 4 would we need to be? And we can see now that here we would need to be within a region here, and so in this particular case our delta would now need to be 1/2. Now this would be the maximum we could be away. We could always say our delta was 1/4, and we definitely would fall within epsilon of L when we would do that, but this is kind of our maximum value we could be to still guarantee that we'd be within epsilon. So if our epsilon was 1, our delta would need to be 1/2 or smaller. Our precise definition of limit then is let f be a function defined on some open interval that contains the number a except possibly at a itself. Because remember, for a limit to exist it does not have to be defined right at a. Then we say that the limit of f of x as x approaches a is L, and we write it like our notation here. If for every epsilon greater than 0 there exists a number delta greater than 0 such that the distance from x to a, so absolute value of x minus a, is less than delta, and we said x can't equal a, so it's going to be greater than 0, then the distance from the function to the limit, what we're going to call the limit, must be less than epsilon. So this needs to be true for every epsilon greater than 0. So essentially what this is telling us is the limit as x approaches a of f of x equals L means that the distance between f of x and L can be made arbitrarily small by taking the distance from x to a sufficiently small but not 0. So we can get f of x as close as we please to L if L is the limit by taking x close enough but not equaling a. So here, if we look at this figure and we say the limit as x approaches 3 of f of x equals 5, and for every epsilon greater than 0 we would be able to find a delta so that the distance from f of x to 5 is less than epsilon whenever x minus 3 is less than delta. So as we look here for a, this says if epsilon was 1, and we can see that we could come over here and see that as long as we had anything between 1 and 5, our function value would be less than 1 away from L, which we said limit, which was 5. So our delta would need to be 2, so that the difference between the x value we choose and 3 is less than 2, but x can't be 3, so that's why it has to be greater than 0 here. Now we could also take this for epsilon equaling 1/2, and we could look at this region and say what would our delta need to be such that the distance from our function value to our limit is less than 1/2. And you can see that as long as I picked a value between 2 and 4, I would fall in this region, and so the absolute value of x minus 3 needs to be greater than 0, so x doesn't equal 3, and it needs to be less than 1. So our delta in this particular case is 1. So we could just keep making epsilon smaller. What if epsilon was 1/8? We could still find a delta such that when we did f of x minus 5 less than 1/8, we would have that if we had x minus 3 less than a certain delta, and you can see in this case that delta would need to be 1/4. And so delta depends on epsilon, but given any epsilon, I get close enough to x so I can find a delta close enough such that my function value is within epsilon of L. So if we wanted to prove that something was a limit, that the limit as x approaches a of f of x equals L, then we would need to be able to find a delta. So we need this connection between epsilon and delta so that given any epsilon, some arbitrarily positive number, we could find a delta so that when we know that x was within delta of a, then we would know that f of x minus L's distance is less than epsilon. Once we find that connection or that delta, then we could write a proof and say for any epsilon greater than 0, we're going to assume that x is within delta of a, and so we would write that relationship, what delta needs to equal in terms of epsilon. And so for example, if we found out it needed to be 3 epsilon, and then you tell me epsilon needs to be 2, then I know delta needs to be 6. If that epsilon needs to be 1/2, then I would know delta needs to be 3/2, and so forth. So let's go ahead and see how this would work. We're going to prove that the limit as x approaches 2 of 2x minus 1 equals 3. So we are first going to look where a equals 2, and we want to prove that L equals 3. And so we are going to say for any epsilon given that's a positive number, any epsilon greater than 0, we need to find a delta, see how close to 2 we need to be, so that if x is within delta of 2, then we know that f of x is within epsilon of L. So let's go ahead and take the steps for finding this. The first thing we'd want to do is a little bit of preliminary work to find the connection between delta and epsilon. So I'm going to take my function, which is 2x minus 1, and subtract my limit, which is 3, and I want that less than epsilon. And I want to find some connection between x and a, and so I'm going to find the distance between x and a in this case is 2. And so this is what I'm looking for. I want this to be less than delta, but I want some connection between delta and epsilon. So I'm going to take this f of x minus L, and I'm going to do a little bit of simplifying. And the next thing I'm going to do here, because I'm trying to get it to look like this so I can see the connection between epsilon and delta, I'm going to factor a 2 out. That would leave 2 times the absolute value of x minus 2 less than epsilon. I'm going to divide both sides by 2. And I can see now that as long as the distance between x and 2 is less than epsilon over 2, then this inequality here will be true, because that's essentially what I used to generate this one. So our delta needs to be epsilon over 2 or less. So epsilon over 2 will work. So now let's go ahead and write up the proof. So we're going to say given epsilon greater than 0, choose delta equals epsilon over 2. So then we will have if the distance between x and 2 is less than epsilon over 2, then we know that the distance between f of x and 3 will be less than epsilon. So therefore, by the definition of limit, we do know that the limit as x approaches 2 of 2x minus 1 equals 3. Realize then with this statement, this delta depends on epsilon, but you can give me any epsilon, and if I divide that in half, I can give you a delta so that I'm close enough to x that the distance from the function value to L is less than epsilon. One last thing, definition, if we had just a left-hand limit or just a right-hand limit. So left-hand limit, as x approaches a from the left of f of x equals L, if for every epsilon greater than 0 there exists a delta greater than 0, such that since we're only looking on the left side, we only have x between a and going to the left-hand side, so a minus delta, then would imply that our distance between our function value and L is less than epsilon. Now the right-hand limit is the same idea, but our x would be from a, x in between a and a plus delta. Let's go ahead and look graphically at a picture of what that left-hand limit essentially says, and the right-hand limit would be analogous but on the other side. So if we're looking here, limit as x approaches a from the left of f of x, then here is our a value, and we would have L, and we could have L plus epsilon and L minus epsilon, and then we're looking for a delta such that if x is in between a minus delta and a, we know that our function value is within epsilon of L. So there's kind of graphically states that, and of course if we did the right hand limit, we would just look at things on the right side and have a plus delta instead of a minus.